All right, let's go ahead and try a few additional practice problems in calculating the pH. So in this particular problem, I'm going to show you two different ways to solve this. I'm going to use one way where we use the pOH and then another way where we use kW. So here we want to calculate the pH of an aqueous ammonia solution that has a hydroxide concentration of 1.9 times 10 to the negative third. So here's our first way that we can use this. So we'll use pOH. So we know that pOH is equal to the negative log of OH minus. We're substituting in, we have the negative log of 1.9 times 10 to the negative third molar. So when we plug that in, we get pOH is equal to 2.7. Well, we also know that pH plus pOH is equal to 14. So that means that pH is going to be equal to 14 minus pOH. So substituting in, we have 14 minus 2.7, which equals a pH of 11.3. So our pH is greater than 7, so this solution is basic, which you would guess based off of the hydroxide ion concentration. So you could use pOH and then convert it to pH. The other way that you could solve this problem would be to use kW. And again, you'll get the exact same answer. So here, where you'd start out is you'd say, all right, I know that kW is equal to H3O plus times OH minus. Well, in this case, we know the hydroxide concentration. So we're going to be solving for the hydronium concentration. So we can say that the hydronium concentration, H3O plus, is equal to kW over OH minus. So substituting in, kW is a constant for us, 1.0 times 10 to the negative 14th, divided by our hydroxide concentration, which is 1.9 times 10 to the negative third molar. And so we plug that in, and we get the concentration of H3O plus is 5.26 times 10 to the negative 12th molar. Well, if we're trying to find pH, we know that pH is equal to the negative log of H3O plus. So we can substitute that concentration in. So we have the negative log of 5.26 times 10 to the negative 12th molar. And upon plugging this in, we'll get the pH is equal to 11.3. So it doesn't matter whether you choose to use the method where you look for pOH and then convert to pH, or you start with kW and you find the concentration of hydroxide, you're still going to end up finding the exact same pH. All right, let's go ahead and try another problem. So in this problem, acid rain is a serious concern because most species of fish die in waters having a pH lower than 4.5 to 5. So we need to calculate that hydronium concentration in a lake that has a pH of 4.5. Well, so far all we've done is we've calculated pH from the hydronium concentration. So this way we're actually going to be working backwards. So we know that pH is equal to the negative log of H3O plus. Well, if we're trying to solve for this, then we need to get rid of our log base 10. So what we can do is we'll have H3O plus is equal to 10 to the negative pH. Plugging in, we have 10 to the negative 4.5, which is equal to 3.2 times 10 to the negative 5th molar. So that is the concentration of hydronium in a lake where the pH is 4.5. If you've never had to get rid of a log before, on most calculators today, what you do is you'd hit second and then log, log, log base 10, not natural log, and that will give you this 10, and then you can just plug in negative pH. Again, this negative sign here, very important, otherwise you're going to end up with an erroneous value.